Hi students, welcome to Science Extension and Module 1, the Foundations of Scientific Thinking. This is video number 9 and we're going to be looking at paradigm shifts. The specific learning intention for this video is for you to select one example from the following list to analyse the paradigm shift and how evidence is used to support new theories to explain phenomena and their consequences. And the 4 examples you have to choose from are Lavoisier and oxygen, Einstein and general relativity, Wagner and continental drift leading to plate tectonics, or McClintock and transposable elements, also known as jumping genes. Now I'll go through all 4 of these examples in the video, so obviously you just need to switch through to the one that is most relevant to you. It's not necessary for you to have all 4 examples. So we'll do a general introduction first to Thomas Kuhn and what a paradigm is and why paradigm shifts are important. We'll look at a couple of different types of paradigm shifts and some of the ways that science moves forward under the Kuhnian model, and also then look at some specific examples of paradigm shifts, both so you can write about them, but also so that you can explore one in a little bit more detail. As always, I've tried to use a range of different sources. These are the general sources. Obviously, when you go into each of the examples in more detail, it's important that you add additional sources to what you're looking at. But the book from which most of this material has emerged is Thomas Kuhn's Structure of Scientific Revolutions. You'll also find some summaries in Okasha's Philosophy of Science and also in Chalmers' excellent book, What is This Thing Called Science? So what is a paradigm? Well, Chalmers describes a paradigm as something that is made up of the general theoretical assumptions and laws and the techniques for their application that members of a particular scientific community adopt. So it's the overarching framework in which we work. Changing the paradigm then is a fairly big deal, and it hasn't happened that often, but it's happened enough that we can get a bit of an idea of some of the forces that drive both the prevailing paradigms and also the reasons why they might need to shift. So Thomas Kuhn examined the scientific paradigm through the ages, and he defined 2 different types of scientific endeavors. The first is normal science. That's the day-to-day practice of science and the development by accumulation. So everyone doing lots of different experiments, everything confirming what we already know or within the theory that we have about a particular area of science. The experimental observations are consistent with that theory. So all of these scientific observations and experiments, the generating of data and observations, the testing of hypotheses are all sitting within this kind of day-to-day practice and are consistent with the prevailing paradigm or the prevailing ideas about science at the time and in that particular discipline of science. But then Kuhn also described this puzzle-solving science. That is, episodic upheavals in science, where continuity is interrupted by periods of scientific revolution. Now, these are quite emotive words, and they basically describe the fact that occasionally in science what we've seen is experiments or ideas that seem to contradict the prevailing theories. Experiments that can't be explained by the theory of the day, that need something different, that need maybe a slight tweaking or a major modification. So when scientific observations can't be explained by the contemporary paradigms, or anomalous results or hypotheses aren't supported by experimental observations, then we need to start thinking. We need to start solving the problem, and maybe the solution to the problem is a different paradigm. So paradigm shifts and scientific revolutions generally take one of 2 forms. Kuhn has described theory replacement, in which new theories replace old theories. One example of that might be heliocentrism replacing geocentrism. So the idea that the universe revolved around the Earth being replaced by the idea that the solar system has the sun at its center. Kuhn also talked about theory modifications. That is, new theories are added to contemporary theories. An example of this traces forces and motion. So if we think about Newton's laws of motion and gravitation, they were building on Galileo's and Kepler's discoveries, and then Newton's ideas were then extended by Einstein's theory of special and general relativity. Einstein's theories did not replace Newton's laws, but are used in those special circumstances that demand high levels of accuracy and when classical mechanics fails. And that usually only happens when objects are moving close to the speed of light. So then, how do we get these paradigm shifts? Well, according to Kuhn, normal science does not produce scientific revolutions. Instead, revolutions are precipitated by puzzle-solving science. Over time, observations which cannot be explained by contemporary paradigms emerge. To explain these discrepant observations and anomalies, new theories need to be developed. These new theories then constitute a paradigm shift. Kuhn also identified a three-step process by which scientific revolutions occur. He identified periods of normal science. That is, normal scientific investigations occur within the purview of contemporary science paradigms. Normal science can also be preceded by pre-paradigmatic stage. That's a period where we have a little bit directionless, a little bit inchoate, a time where things aren't really clear but don't look necessarily like they're completely aligning with the prevailing paradigm, but hasn't really generated enough data for us to move into this next section, which Kuhn has described as crisis. So over time, anomalies and unsupported observations begin to accumulate. The contemporary paradigms are critically evaluated and there's an increase in puzzle-solving science activities. And this is the period known as crisis. And it's what leads to the paradigm shifts, where newer theories are proposed to account for the puzzle-solving scientific observations. So where things didn't fit within the current paradigm, that's when the new paradigm is designed to explain both all of the observations that have preceded it, so everything that must be part of the original paradigm, plus the anomalies that have been identified that don't fit the previous paradigm should be able to be explained by the new paradigm. It's probably important to make sure whichever of the four you're going to delve into in a little more detail, that you have a bit of an idea about some of the key paradigm shifts that have occurred. So probably the best one to talk about, we can talk about the Copernican revolution, which is basically that idea of shifting our thinking from the Earth being the center of the universe, and therefore humans, or me, as the center of the universe, to the universe doesn't revolve around me. The planets don't orbit the Earth, they orbit the sun. And so there's a few anomalies that started to be looked at that were not easily explained. So the retrograde motion of planets, that is when they were moving in the reverse direction to the way apparently that they should be going. And so we did see them kind of appearing to drift backwards before they moved forward again. And that was an interesting thing to explain if the Earth was the center. The orbit of Jupiter's moon, so when Galileo observed through his telescope objects appearing to orbit Jupiter, that suddenly started to make people think about the fact that not everything was orbiting around the Earth. And also when Galileo observed the phases of Venus. And again, that can't be explained if the Earth is the center, but it can easily be explained if the Sun is the center and both the Earth and Venus are orbiting the Sun. This led to this important paradigm shift around heliocentrism. But we've also seen some significant paradigm shifts in the area of biology, in Darwin's theory of evolution by natural selection. So evolution wasn't Darwin's idea. The idea of change over time well preceded Darwin. But what he looked at was this idea about the inheritance of acquired characteristics, that is, things that were passed on from one generation to the next being driven by environmental factors, was a Lamarckian idea and not supported by Darwin's observations. So he noticed the experiences within a lifetime were not inherited. That is, if you lost a limb at some point, particularly through maybe a conflict, that your children were born with normal limbs. They didn't have that particular lost limb that you might have lost. Darwin also noticed that complex organisms are not formed directly from simpler ones, and started to think about some of the ways in which this might occur. His idea around variation, selecting agents, selecting pressures in the environment that preferentially select some individuals over others and that can therefore change populations over time, was later supported too when we understood more about the genetic particle theory of inheritance, which was really started by Mendel's work. So this was another significant shift away from the Lamarckian evolution through acquired characteristics into evolution via natural selection, survival of the fittest, as it's more commonly known. That idea of Darwin where we have variation in populations, a selecting agent that preferentially selects some individuals over others, and the reproductive phase that allows those preferential genes to be inherited in future generations and shift the populations over time. A third example that you might want to consider is the miasma theory of disease. That is, diseases are caused by bad air. But then we had Pasteur's experiments with swan-necked flasks and the idea that life didn't spontaneously generate, that it actually had to come from organisms. So things spoiled not because they automatically went bad or they generated new life, but because there were bacteria or some sort of microorganism that we couldn't see that was actually getting into the food or on the food, and as a result of that was reproducing and therefore making the food spoil. We also had Koch's postulates about microbes and disease and the link between the causes of a particular disease and a particular pathogen or microorganism that maybe caused that disease. That led to the paradigm shift of the germ theory of disease. So no longer did we need to blame bad air, we actually had a theory of the cause of different types of infectious diseases. At this point, you need to move on to one section of the video that focuses on what you're most interested in. So you'll find information about Lavoisier, you'll find information about Wegener, about McClintock, and also Einstein in the next few sections.